Let's look at doing interpolation of tabular data. Here's an example we might want to solve. We're given this table of data where we have values down the left side, those are down a row, and across the top in the columns. And the interior purple values correspond to values for the rows and columns. So for example, if I say the row value is 8 and the column value is 14, I would go in and that would correspond to the interior value of 4. Well, what if I want a value that's in between? See, I want to know what if it's 9 and 20? Well, that lies somewhere in here. The value's not in the table, but I can use tabular interpolation to find that value. Now, of course, you could brute force this by hand, but there is a methodical method you could use, and that's what we're going to discuss here. In this interpolation method, we start by finding the bounds for the values. So 9 is bounded by 8 and 12. 20 is bounded by 18 and 22. And the value corresponding to 9 and 20 is some linear combination of 6, 8, 15, and 20. It's the interpolation of those four values. This now, as I've drawn here, is the section of the table that we're interested in. We want to know what happens when we pick 9 and 20. You can see we don't need any other data values from the table. We only need the corresponding row, column values, and the interior values, which I'm going to call the z values. The method we're going to use is a geometric method that's based on weighting. You draw a square within these values. We want to have a linear combination again of 6, 8, 15, and 20. That will give us the interior value that we're looking at, which is going to be right there. That will correspond to row is equal to 9, column is equal to 20. Partition off the square and calculate the size of the square. The square is 8 on the top, 12 on the bottom, 9 at the dashed line. That means this distance is 1, this distance is 3. 8 to 9 is 1, 9 to 12 is 3. Across the top, it's 18 to 20, that's 2. 20 to 22 is 2. Next, calculate the area of each of these interior pieces. This is 1 times 2. It has a total area of 2. This is 2 times 1, total area of 2. 2 times 3, this is 6, and this one corresponds to 6. Now, based on these areas, we're going to weight the corresponding 6, 8, 15, and 20 to get a linear combination. The weighting comes from the rectangle that's opposite of the corner. I'm going to write down the weights. 15 is weighted by the 2. 20 is weighted by its diagonal, the 2. 8 weighted by 6. And 6 is weighted by 6. Now we need to normalize that whole thing, so we're going to divide by the area of the whole thing. The whole side is 3 plus 1 is 4, 2 plus 2 is 4. So we divide that whole thing by 1 over 4 times 4. And that gives the value for the interior point. If you do the math, that's 9.625. Let me formalize this method. Given a set of tabular values where we have x and y and corresponding z values, and we want to find the value corresponding to an intermediate x and y, we identify the bounds for x and y values. I've written them here as x1, x2, y1, y2. And the corresponding z values, tabular values, z11, z12, z21, and z22. Now to simplify the notation, I've numbered the 4 z values, 1, 2, 3, 4. This is arbitrary, you could number them anyway. The key is that I've also numbered the areas corresponding to this internal rectangle, where A1 is opposite of the corner 1, A2 is opposite of the corner 2, A3 is opposite of the corner 3, and A4 opposite of the corner 4. Now we can create weighting values. W1 is equal to the area of 1 divided by the total area, where the area of 1 is equal to y2 minus y times the height x minus x1. In doing this, I'm assuming that y1 is less than y2 and x1 is less than x2. W2 is equal to area 2 divided by the total area, where area 2 is the width, which is y minus y1, times the height, which is x1 minus x. W3 and W4 are similar. AT is the total area, x2 minus x1 times y2 minus y1. Now we can calculate the interior z value by using the weighting matrices as follows. Z interpolated is Z2, 1, that's on the 1 corner, so we use the W1 weighting matrix, plus Z2, 2, that's on the 2 corners, so we use the W2 weighting matrix, plus Z1, 2, that's on the 3 corners, so we use the 3 weighting matrix, plus Z1, 1, again, that's on the 4, so we use the 4 weighting matrix, which is W4. And that will give us the corresponding value for Z. You should take this formula, apply it to the data in the previous example, and make sure you understand how it works.